thank you very much for the introduction. This is joint work with Tibor Jager. Well, my talk is about a very common mechanism in user-centric cyber-physical systems, which is called point accumulation. You can also call it incentive collection if you want. Here are three typical examples where this mechanism is deployed. So you have loyalty systems, crowd sensing systems, vehicle to grid. And how does it work? In a loyalty system, you all know about loyalty systems. You get points for every purchase you do, right? In reward for your loyalty to a shop or something like that. You basically have the same mechanism over there. There you get incentives for sharing collected data that you measured with your smartphone, like health data or like environmental data, which is typically enhanced with location and time. And yeah, you also have this mechanism here. You just replace collected data here with the power your e-car supplies to the smart grid. So everywhere you have this basic principle here, and privacy is of course an issue in all these scenarios. So on all levels, especially also with respect to the point accumulation mechanism. Why? Because, for example, in this scenario, an operator, if you do it naively, an operator could learn where and when you purchase items, or here it could learn where and when you have been when you collected data with your smartphone while walking around. So what's the state of the art in privacy preserving point accumulation? Well, there's not much, at least that I'm aware of. Especially there is no dedicated formalization of this widespread building block, which is unfortunate. It just appears implicitly as part of some bigger systems like V2G systems or crowd sensing systems. So what's the situation here? Well, it's not much better. Many of the systems actually use crypto, but they lack formality. So there are no models, there are no proofs. So what that means? It means that actually most of the time you cannot be sure at all which attacks a system you consider should actually protect from, right? So all you can do is hope that it satisfies some vaguely defined notion of security. So we try to do it better, of course. So we formalized the minimal functionality of such a mechanism. We did a privacy model, a security model. We came up with a generic construction from abstract cryptographic building blocks, which of course satisfies our security formalizations. And we also presented an efficient instantiation. So probably some more about our framework. So to keep it simple, we try to formalize a token-based online non-interactive system. What does it mean? So token-based means there is some cryptographic object which roughly represents kind of a piggy bank with which users can accumulate points. Then you have a bunch of non-interactive algorithms which can create, modify or verify these tokens. And finally, online means that so in the actual system later on, you have to assume that there is some central database which contains the already redeemed tokens for double spending purposes. So what are the parties of our system? We have some trusted third party, which is actually needed only once to set up some system parameters honestly. Then we have users which like to collect points. We have issuers who issue these tokens, these piggy banks. Then we have an accumulator, and she adds points to our token, and we have a verifier which verifies and redeems the points. So some more details about our system. So as I said, the trusted third party set up some common system parameters, so the common reference string. Then we have the issuer who generates a public and secret key, where the secret key is shared between the issuer and also the accumulator. How does the system work? Well, to issue a token, the issuer wants some algorithm issue with his secret key and a serial number for the token. The user checks the token. To accumulate, the user first blinds this token, where this operation yields, besides the blinded token, an unblinding trapdoor. The accumulator now operates on this blinded token using its secret key and the value vi it wants to add. When the user receives the updated token, it unblinds the token using the unblinding trapdoor, updates its balance. And to redeem a token, again, the user has to prepare a new token, a verification token, which in our case is again some blinded kind of token. Then it sends over the verification token, also the claimed serial number and balance, and the verifier checks everything. So how do we define privacy in our setting? Well, first of all, what do we like to achieve? So roughly speaking, we like to have unlinkability of user transactions with respect to a colluding issuer, accumulator, and verifier, where we still assume that these guys send valid tokens. Otherwise, it would be probably hard to achieve such a security notion. How do we define that? We use the real-world, ideal-world paradigm. So that means we demand that there is an ideal world which is indistinguishable for the adversary from the real world. And in this ideal world, there is no information leaked which helps the adversary to link transactions, except for the total amount on the token when the user redeems the token, but this is done intentionally. So what does it mean more practically? It means that all accumulation transactions, all accumulation transactions which actually lead to the same total amount are equally likely for an adversary. Probably some more details on that. So this is basically the real world where, as I said, the issuer, the accumulator, and the verifier collude to link transactions, right? So, and in theory, it's possible to link transactions. For example, consider this link here. Why is it possible? Because this blinded token is of course associated with the token the user receives from the issuer, because it's derived from it using this blind operation. Okay, so what do we do in the ideal world? Well, we demand that there is some simulation setup algorithm which generates, besides a common reference string, also a simulation trapdoor, such that the CIS looks like a real CIS. And the simulation trapdoor can be used instead of a real token by simblind and simprepare to generate a blinded token and a verification token. Right? So now, of course, there is no link at all between this guy here and this guy here, because we just deleted the token. Okay, this is a security game. It's also pretty simple. The adversary can ask for new tokens repeatedly. It can also ask the accumulator to add points to his tokens repeatedly, where this is allegedly a blinded token, but it can also be something completely different. In the end, it should come up with some verification tokens, some claimed serial numbers and balances, and it wins if the tokens verify and if the adversary successfully claims more than what was actually issued. Okay, some more words about our construction. Well, we used some standard cryptographic building blocks like commitments, signature schemes, and non-interactive zero-knowledge proof of knowledge. So I can't formally define these building blocks here, but just a few words. So with a commitment scheme, you can commit to a value such that this value is hidden, but you can also not later change the value when you open the commitment. Then we need that these commitments are re-randomizable. We also need that these commitments are additively homomorphic. This means if you have commitments to two values, then you can somehow combine these two commitments, like for example multiplying them, and the result will be a commitment to the sum of these of the contained values. We need regular digital signatures, and we need this NIST POCs. So what is a NIST POC? Well, it's a complicated tool, but basically you can with this tool you convince someone that you know some secret satisfying a certain relation, like you know the DL of a public group element, such that nothing else is revealed about the secret. So how do we use it in our setting? Well, first of all, the issuer simply generates a simple signature key pair. Then to issue a token, we simply commit to the serial number. We also commit to the initial balance, which is 0, and then the issuer signs these two commitments. This is our token. The user verifies this token. So to accumulate a token, the user needs to blind it, right? So what does he do? He simply re-randomizes the two commitments and shows that he does correctly. That means he shows that he knows some original commitments, C1, C2, for which he knows, for which he has a signature. So he shows that he knows some authenticated token, and that these commitments C1 prime and C2 prime are just some re-randomizations of these original tokens. So this is sent over, and of course verified if the blinded token is well formed. Then the accumulator actually again issues a new token where she keeps the commitment to the serial number she just received, and to generate a commitment to the updated balance, she uses the homomorphic property of the commitment scheme. And then again she signs everything, and that's it. And the user just needs to verify this token, but he doesn't need to unblind the token because it's unblinded again. So much about our construction. Some words about performance. So we instantiated our generic constructions with an optimal structure preserving signature scheme from Crypto 2011, and with GS commitments and proofs 2 minutes. Right, and for this concrete construction, we did some estimates for 128-bit security, which is rather high security, and assuming a lower cost NFC smartphone as a platform for all algorithms, so for user and issuer accumulator algorithms. And this is the result. Well, it appears to be fairly efficient because the runtimes of all algorithms is below 500 milliseconds. You can also see that probably the accumulation protocol will be the most time consuming. But even if you add up the runtimes on the user side, on the accumulator side, and the communications cost, you should be still below a second in a real implementation. So time to wrap up. What did we do? We proposed a formal framework in instantiation of a provably secure black box accumulation scheme. So what remains to be done as future work is quite a lot, in my opinion. First of all, you can try to improve efficiency of our current instantiation by replacing these costly GS proofs by hash proof systems, which is only possible in certain situations when the issuer and the verifier are the same entity. But you can also try to improve the applicability of our scheme, for example, by allowing negative points, which would be useful in scenarios such as reputation schemes where negative points represent bad ratings. And for this, you of course need to incorporate a mechanism which forces the user to show only its most up-to-date token, because otherwise he can just drop bad ratings by showing all tokens. Okay, this concludes my talk.